Hello guys, welcome to my video. My name is Abul Fazl, and in this video we are going to solve two-dimensional Laplace equation in Cartesian coordinate numerically. If you remember, in the previous video we solved this problem, the two-dimensional Laplace equation analytically. Then we restrict our problem to some area with well-defined boundary condition. Then, applying boundary condition, we got such a solution for the function uxy. Then we plot it in Matlab, and here you see the results. If you are interested to see how we obtain this result, you can find it in these links. Now, I'm going to solve same problem using finite difference method. Generally, the finite difference method utilizes the definition of derivative. Imagine you have a function ux, and this function is infinitely differentiable and well defined in all points. The derivative of this function with respect to the x is nothing but the limit of the value of function at point x plus delta x minus the value of function at the point x divided by x plus delta x minus x. And if we tend this delta x to 0, we can approximate this by this function, and this is ux plus delta x minus ux divided by delta x. Here, if you imagine that this delta x tends to 0, so this line, that is just a slope, will tend to this exact solution for the derivative function at the point x. So, based on this, we can define different kind of finite difference for the first order derivative. Now, for simplicity, let's replace these points with some indexes, and each indexes indeed shows the value of x. So, based on this definition, we can say that the derivative function with respect to the x in the point I, and this point, is the value of function at the point of I plus 1, this point, minus the value of function at the point I divided by delta x. And this is known as the forward finite difference. Then, in the other way, we can also define the derivative function with respect to the x at the point I utilizing the previous point. I mean, the derivative at this point is just the value of function at the point I minus the value of function at the previous point divided by this interval, and is known as the backward finite difference. Another is the central finite difference, and it is the value of function at the next point minus the value of function at the previous point divided by this interval, and this is 2 delta x. So the first derivative of a function with respect to a parameter, with respect to a variable, we can replace with these definitions: the forward, the backward, and the central finite difference. What if we have the second order derivative? Let's see how we can find the definition of second order derivative in finite difference method. For this, I'm utilizing the Taylor expansion of a function. Based on the definition, the Taylor expansion of a function ux around the point A is just ux plus a equal to ux plus the first derivative divided by 1 factorial multiple to the a plus the second derivative divided by 2 factorial multiple to the a square, and plus the third derivative divided by 3 factorial multiple to the a cube. Now, if I replace this a with minus delta x, what I have is this. ux minus delta x is ux minus first derivative delta x, second derivative delta x square, and the third derivative delta x cubed divided by 1, 2, and 3 factorial respectively. And here we have minus in the odd derivative. And if I replace the a with delta x, with plus delta x, what I have is ux plus delta x equal to ux plus first derivative plus second derivative and plus third derivative, right? If I add these two functions together, what I have, this is just ux plus delta x plus ux minus delta x equal to, I have two ux here, right? Then the first derivative will cancel each other, but the second derivative will remain, and we have 2 times of the second derivative divided by 2 factorial multiple to the delta x square. And also the third derivative cancels each other, and we neglect the higher order derivative because we say that delta x is a small value, and so we neglect the higher order of delta x. And if I bring this part to the left, what I have is ux plus delta x minus 2ux plus ux minus delta x. It's equal to these two cancels each other, and it will remain the second derivative multiple to the delta x square. And if I divide the both sides of the function with delta x square, I have the second derivative with this equation, and this is ux plus delta x minus 2ux plus ux minus delta x divided by delta x square. And this is the definition of the second order derivative in finite difference method, right? And if I express it as using the indexes, it says that the second order derivative of function with respect to the x at the point a, this is just the value of function at the next point minus the value of function at the present point and plus the value of function at the previous step divided by delta x squared. So we define the first derivative and the second derivative in finite difference method. Imagine that we have this x-axis, and we discretize to this axis to the point, and we assign some indexes to each point. And we imagine that this point and this point is our boundaries, and the boundary condition is well known at this point, right? So imagine that this first derivative becomes some known parameter. So if I simplify it and try to find the value of function at point I that is unknown, so this is simplicity. This is simple p delta x, that is known value, plus u I minus 1. It means that we have some known value delta x and p, and if we want to calculate the value of function at the point I, it's enough to sum this parameter with the value of function at the previous point. And from boundary condition, you see, we have the boundary condition. So this is known, we can calculate this unknown value. What about the second order derivative? If it's become equal to some known parameter, and if I simplify it and try to find the value of function at the point I, what I need to know the value of function at the previous point. This is known from boundary condition. Moreover, I need to know the value of function, this one, at the next point, right? And this is the known value. I have this, but I don't have the value of function at the next point. And using the finite difference method, I'm trying to find the value of function at the next steps, at the next points, right? But I have not this. If I want to calculate the value of function at this point, I should know the function ux, but I don't know. So what can I do? Indeed, to overcome to this, we need to have some initial guess. We imagine that the value of function at each point have some value, and we guess some value, right? So if we have some guess here and we have the boundary condition, so using this we can calculate the value of function at this point. But because this value is just some guess and maybe it has some large uncertainty, right? So this value will have some error. Moreover, if I want to calculate this point, I need to use the previous point and the next point, this one, right? And again, because there is some uncertainty here and some uncertainty here in solution, so the obtained result will have some uncertainty, will have some error, right? And to overcome and to reduce this error, in this method, people usually use the iterative method. It means that we solve this value inside the loop for many times to reduce the error. I will explain it in coding part. If we write some code, I think it will be more clear. I will show you how does it work. So we want to solve the problem at the same area with the same boundary condition that we solve it analytically, right? So for x-axis, I'll define the index j, and I discretize this x-axis, and I assign j with each point. And the y-axis, we define any point with the index of I, right? So if any point uij here or uji, no matter, will represent the value of function at that point, right? uxi will be equal to uij or ji. But here, because j represent the x-axis, it should be uji, right? If I substitute what we derive for the second derivative here in this our partial differential equation, so based on definition, we have the value of the 2 times a value of function at some point ij, right? We have uij here, plus the value of function in some constant I, right? In some constant I, and j plus 1, also the value of function, again, at the same constant I, but one point before the point j, and this is j minus 1, right? And again, the derivative with respect to the I should be calculated 2 times a value of function at some point ij plus value of function at some constant j, because here j represent the x-axis and the derivative is with respect to the y. So here the y should be changed, and the j and the I index here represent the y-axis. So we change the I, and based on definition, the value of function at some constant x or some constant index j, and the value of function at the point I plus 1 in some different point for y. And if I simplify it, I have delta y square multiple to this value plus delta x square multiple to this value, and the numerator of this should be equal to 0. And if I factor out the 2ij here and 2ij here, what I have is minus 2ij multiple to the delta y square, and here I have minus 2ij multiple to the delta x square, and I have the same terms here, delta y square multiple to the uij plus 1 plus uij minus 1, and here I have delta x square multiple to the ui plus 1j plus ui minus 1j equal to 0. And if I simplify it and try to gather uij in some side and the other term in the other side, I have this, as you see here. And if I divided the both part of the equation with 2 delta y square plus delta x square, what I have is uij equal to delta x square multiple to the ui plus 1j plus ui minus 1j plus delta y square uij plus 1 plus uij minus 1 divided by 2 delta x square plus delta y square, right? So we found out that if we want calculate this partial differential equation numerically, it's enough to find the value of function at each point using this definition from knowing the value of function in the neighboring point, right? Okay, so we had this analytical solution, we solve it analytically, and this is the analytical answer for this partial differential equation in this area. And we have the numerical solution for the same partial differential equation. So let's now go to the Matlab, and first let's plot this analytical function, then calculate the numerical and plot it and see how they are close to each other. And here, for simplicity, I define omega with 1. It's just equal to 1, so I don't take into account the omega in the equations. And I put a to become 3 pi and b become just pi. So here, let's go to the Matlab and plot the analytical function, then calculate this one. So I have Matlab opened here. I define new editor file. So as usual, I start with clc command. It's clear the command window. Clear. It's clear the cache and close all the open figure. So we say that omega is 1. We don't take into account it and define a to be become 3 multiple pi, right? And b equal to just pi, right? And then let's define the number of points in the x-axis. We defined it with nx. Let it be 100. Then number of points in the y-axis, and let it be just 50, right? And so let's define the delta x with dx. I define delta x with dx. It should be a divided by number of points in the x-axis, and dy, the step point in the y-axis, which is just b divided by number of points in y-axis, right? Okay, so let's define the x and y. X should be changed from 0. I want to define the area that I'm interested to solve the differential equation in this area. So x should be changed from 0 with the dx step until a, and y should be changes from 0 to with dy step to b, right? Okay. Also, in previous video, I explained that we can find this in two ways: finding this function inside the loop, or using the mesh grid command. I used the mesh grid command in the previous video, so in this video I will solve it inside the loop. So I want to define index I that represent the y-axis, so it should be changed from 1 to n number of point n y plus 1 in y-axis, right? And here index I represent the y-axis, and it changes from y1 to n y plus 1. And also j that represent here the y represent here the x-axis should be changed from 1 to how much? N x plus 1. And right. Okay. Okay, so what is my function? I define it with u, and it should be I, j. uij is just sine x divided by sine a. Sine x, and this is the array x j, right, divided by sine a, right, multiple to the sine hyperbolic y, and this is not a scalar, this is the arrays, and y I, it should be yi because I represent the y-axis, divided by sine hyperbolic. I should put that here, sine hyperbolic b. And here you see that this this underlined with some orange line, you see here, and it should state that u is not defined here. So let's define some memory for u, and we say that okay, u is zeros and y plus 1 and n x plus 1, right? And I want to plot this function. I want to, in a normalized mode, I mean I find the maximum value for the u, and I call it with max u. Max u is just max of our matrix, one empty bracket, in all rows and columns, and I define normalize u to become the u divided by max u, right? Okay, let's save it. Goes to the editor file and save as some, it's the third code that I write, analytical numerical two-dimensional Laplace. Save it. Okay, and let's plot it using counter command. Contour F, normalize u, number of counter 200, and line of line color for contours. I don't want any color, so it should be none. Then let's define the color map. Indeed, the color map plot my function in the some family, and I here choose the jet family. This some it is just some colors, and the maximum number of color in this family is just 265 or 56. I think it's 56, 256, right? And here, what else? Color bar. I want to define the color bar on the side of my plot, and also the minimum and the maximum value for color bar. It's c-axis. The c-axis should be changed from -1 to 1 because I normalized my function due to the maximum value. So the minimum value for this, it could be just -1, and the maximum value could be the +1. Let's run it and see, is it okay or not? Okay, but there is some error. Color bar here, color bar. It was just misprinting. Okay, and you see the same that we had here. Here you see this plot, but at the previous time I plotted it using mesh grid command, and that's also simple. You can use that, no matter. Okay, and let's here define the title. Title here, I want to be analytical, right? And let's define X label. X label is just X, right? And Y label is just simply just Y. And again, title, I think title. Yes, we have analytical. Now we plot the analytical solution for two-dimensional Laplace equation. We have this law. So let's go to the numerical. We want to calculate it numerically and plot it. Numerical part, right? So what I have for numerical, let's go back to the slides. This is the numerical solution. So we have some coefficient here. You see this is 1 divided by 2 delta x squared plus delta y squared. So I define it with some coefficient. I call it with CO, coefficient. This is just 1 divided by 2 times of dx squared plus dy squared, right? I just define it as a coefficient row. So what else? I define the coefficient. Let's define the boundary condition. Okay, we have coefficient, and then let's define boundary condition. And before that, let's allocate some memory for you. I want to for numerical part, I define this with the capital U to be different from the numerical, to become different from the analytical. So I allocate some memory, and this is zeros, n y plus 1 and nx plus 1, right? And this is indeed our initial guess. We say that we should have some initial guess. Here, this u represent play the role of initial guess also. And so that's our initial guess. We imagine that the value of function is 0 everywhere. And let's define the boundary condition, the capital U. And what was the boundary condition? The boundary condition is that at the left boundary, you see at the left boundary, this is 0, right? Or let's start from this. At the lower boundary, this is 0 again. So it says that and index 1 here in that represent the 0, because in Matlab we cannot define 0 index for a matrix, so index 1 represent the 0. In the first, it means that in the first row and all column, you see, in the first row, in the 0 row, and for all column, this is 0. This is the meaning of this command. It should be equal to 0, right? And also it says that in the upper boundary, it should be sine x divided by sine a, because we defined omega equal to 1, so it's sine x divided by sine a, so it should be at n y plus 1, and all in the ny plus 1 row and all column, it should be sine a sine x, right, divided by sine a. right? And left boundary, it should be U at all. The left boundary, it says that at all rows and the first column, all rows and the first column, it should be 0. And this command, where is it? This command, all column and the 0 rows, first rows, it should be 0. And by the same way, at all the all rows and the nx plus 1, it is just sine hyperbolic of y, right, divided by sine hyperbolic of b, right? Okay, so this is, let me here also make the comment, initial guess. Our initial guess is just 0 at every point, and we define the boundary condition. Let's check it. Right. Okay. And this is our boundary condition. What else? What else? Okay, nothing. Let's put it inside a loop and calculate at every point, point by point. Okay, for I from 1 to n, I represent the, we say that I represent the y and y, right, from I equal to 1 to ny, and for j that represent the x-axis, it should be changed from not 1, because 1 is our boundary condition and we are interested a point after boundary condition, so it should be 2. Also it should be 2, and at the end our boundary condition is ny plus 1 and nx plus 1. So here we are going to calculate it 1 point before the boundary condition, and this is should be ny, and it should be changed from 2 until to nx, right? Right, and what we have, it should be capital U, I, J, right? Capital U, I, J, it should be coefficient multiple to the this one, delta x squared multiple to ui plus 1j plus ui minus 1j. So dx squared multiple to the u I plus 1j, I plus 1 and j plus u I minus 1 and j, right? Okay, plus dy, it should be squared, yes, dy squared, and here it should be dx squared, dy squared multiple to u. Now this time it should be I and j plus 1 minus u I and j minus 1. Semicolon here. I think something, let's check the number of parentheses here. Right. Okay, I think everything is okay. Here should be a 2 multiple, and it should be multiple sign here. Yes, now this orange lines disappeared. And let's use the same command for plotting. I just copy it from here, Control C, Control V, but this time it should be capital U. Maximum capital U is derived from the matrix capital U, and normalized capital U also should be capital U divided by maximum of capital U, and here should be capital U, and here should be numerical, right? Numerical. And let's define a figure here. Figure here to have the both plots, analytical and numerical. Let's check is everything fine or not. There's some error, so it should not be 0, it should be 1. Okay. Okay, and you see, this is the numerical solution, and if we compare this solution, you see they are not similar at all. So what's the problem? The problem is that, let me show you the numerical solution, and this is the capital U. Here from home, open variable. If I opened U, this is the U matrix, you see? This is boundary condition at the upper boundary. This is the boundary condition at the right boundary, you see? And if you look at here, you see that we have solution only for this rows, just a row before boundary condition, and also we have solution here, a row, a column before the right boundary condition. And here we should use the iterative method to update the other point in the matrix. So I should put it inside another loop for k equal to from 1 to iteration number, iter underline number, and end here. And what is my iteration number? Iter underline number. Here I define the number of iteration that I want to solve this problem. Inside the loop I put it equal to 1. Let's check it. I press F5. Yes, everything is 5. You see we have the same because the iteration number is 1. You see they are same. Let's increase the iteration number 2. F5. You see the plots are almost the same. There's not big difference, but if you look at the matrix for the U, you see that also this row and the row 49 and the column, this column 99 also updated, right? And if I increase the iteration number more, for example 10, F5, you see we update the other rows and columns. So let's here define the error, calculate the error between the numerical and the analytical. Error, okay, and I define it with E, and E should be normalized analytical minus normalized numerical, right? This is my error, and I'm using again the same commands for plot. I copy it and paste it here, right? Okay, and here should be E, and the title should be error, right? Let's see how much is the error. So I close this window let me replace this. I closed this window and let's see how does error looks like. F5. And this is our error. Let me show you. You see, this is analytical solution, numerical solution, and error between the analytical and numerical. You see, we have a large error for our numerical value, for our numerical solution. And this error is maximum somewhere here, but in the upper boundary, you see it's green, and green is 0. And it says that at the points close to the boundary, you see, to the up boundary, our solution is close to the numerical, but as we go further, you see, the error increase. So let's increase the iteration number more. How much is iteration number here? Where is it? Iteration number, this one, iteration number. Let's increase it to 100 and run it again, F5. You see, this is error, this is numerical, and this is analytical. We have almost the same. It seems that nothing's changed. Let me close this and check the program one time and see what is the rank. Just a moment. I think I found here it should be plus, because in equation we have uij plus 1 plus uij minus 1. This is plus, and what we write it minus. It should be, you see, it should be plus. And it is plus. Okay, let's run it again. F5 for 100 number. Iteration, you see, error decrease. And if we look at the analytical, this is analytical, this is numerical, and this is our error. You see, when we increase the iteration number, the numerical solution get closer and closer to the analytical solution, and our error decrease. So let's increase the iteration number more. I put it, for example, 500. Let's run it again. You see, error becomes 0, almost 0, and the analytical solution become exactly equal to the numerical solution. It seems that there is a small difference, right? Let's increase more, 1000, and F5. You see, error is 0 again, and if we look at the numerical and analytical, they are identical. And this is the way for solving the partial differential equation using finite difference and iterative method. So we here using the iterative method, and if we want to decrease our error more and more, we should increase the iteration number. For example, for 1000 iteration, if I run it again, I put k here to see how much is k in the command window and see how much left from my code to be finished. You see, it changes and it's reached to the 10,000, and error become again less and less, and numerical become exactly equal to the analytical. So if we want increase the time of running, I mean decrease the time of running and increase the efficiency of our code, there are some another method except than the iterative method. And at the next video, I'm going to explain about the other method that used some other way than iterative way, right? So if you are interested in this stuff, so stay with us. Don't forget to like and subscribe my channel. I hope you enjoyed my video, and I will continue the coding with another way, the same problem with another way. Thank you very much.